Good morning, everyone. We'll give it a few more minutes for people to join. Morning, everyone. We're just waiting a few more minutes for people to join. Okay, Sydney, are we ready to go? Let's go ahead. I cannot see the slides, so I'm assuming the slides are up. There we go. Great. Well, welcome everyone to the first of a series of webinars on the importance of artificial intelligence. Thanks to our sponsors, Boston University, the Institute for Sustainable Energy, and the Rafiq B. Hariri Institute for Computing and Computational Science and Engineering. Also the Energy and Sustainability Club at Boston University, and my organization, Gridwise Alliance. Next slide, please. Gridwise Alliance is a membership organization of utilities, tech companies, grid manufacturers, and vendors, all working to articulate the benefits of grid modernization. And I just wanted to let you know about a couple of reports that we recently released over the last couple months. The first is the technology portfolio, which is the beginning of a year-long project where we're going to explore the kinds of technologies that we expect to be deployed on a modern grid in order to provide the functions that I'm going to talk about in a little bit. And this is really designed for stakeholders in the electricity sector who are not technical engineers to describe the kinds of technologies, where they're deployed on the grid, and how they get used. And you may want to refer back to the technology portfolio after today's conversation in case some of our speakers start dropping very technical terms about the technologies on the grid. We likely have described them in this technology portfolio. We also just released a report that's designed to help inform the discussions around the transportation electrification and what kind of grid investments need to be made. So on the grid side, to accommodate this rapid transportation electrification. Next slide, please. As I said, this is the beginning of a webinar series on the importance of AI for sustainability. And on April 29th, the discussion will be around sustainable mobility. And June 3rd, the discussion will be around smart homes and energy justice. So you can register at the BU website here. And we will continue to be talking about AI for the next few months. So next slide, please. I want to start today's conversation about AI and the power grid by talking about how the electric grid is evolving. Our grid is a highly complex engineered network of lines, distribution lines, transmission lines, generation, and end use, with sensors, data controls, and all sorts of technology deployed across the grid. But it was designed to 100 and something years ago to move large-scale centralized generation across transmission lines through stepping down in voltage to a distribution system and then to the end users. Next slide, please. Today, however, we have a whole set of new drivers of the evolution of the grid. These are things like large variable utility scale energy resources, distributed energy resources like rooftop solar and electrified transportation. And what we're seeing here is a change from a one-way flow of electricity from the generator to the end user to two-way flows of electricity moving both from large-scale centralized resources, whether they're renewables or traditional conventional resources, but also electricity moving from the customer side onto the distribution system and then into the transmission system. We're also seeing, accompanied by this two-way flow of electricity, a two-way flow of information. So all along the grid, from the generation side to the end user side, we're seeing the digitalization of the systems and massive amounts of data being generated and transmitted across the system. So what the underpinnings of a modern grid are going to look like are data and a communication system to move that data across the system. But we're also going to see huge amounts of analytical work done either at the device or in the cloud to manage the system in real time. And that's what we're going to be talking about today. So next slide, please. Just a quick, we're going to hear a lot about the transmission and distribution system in the coming discussions. But when we think about a modern grid, we're going to think about it providing some desired outcomes: a decarbonized power supply, always affordable energy. It's going to support beneficial electrification. It will continue to be reliable and increasingly needs to be more resilient to severe weather. And we're also going to see customers who are increasingly demanding choice, both for how they interact with the grid and the kinds of electricity that they use. So this customer choice element is going to be very critical for a modern grid. That means that we're going to have to think differently about how we do our planning. We're going to have increased system visibility, so we know what's happening at the end of the grid, but also the minute variations that are happening across the grid. We're going to have to operate our grid differently, which means that we may need to optimize the data that's being produced in real time in order to meet the variability that may be flowing across the system. We're going to need new ways to engage the consumer and provide different kinds of energy services. And the grid architecture itself may have to change. So the kinds of technologies that we deploy, and also the kinds of regulatory and policy regimes that are incorporated in what we consider the grid architecture. So next slide. We have a great panel today. I'm very excited about this discussion. I'm joined here by Pablo Ruiz, who is a research associate professor of mechanical engineering and an affiliated faculty at the Boston University Institute for Sustainable Energy. He's also the CEO and CTO of NewGrid, a transmission optimization software startup that spun off of the DOE's ARPA-E research project at BU, and he's a senior consultant at the Brattle Group. Also joined by Matt Cromer, who leads the grid integration research activities at the Fraunhofer U.S. Center for Manufacturing Innovation. His research focuses on developing and piloting software and systems that enable the deployment of distributed energy resources. You may hear people refer to distributed energy resources as DER in this conversation. Matt's recent work has demonstrated novel approaches to using battery energy storage, solar PV, and flexible building loads to support the deployment of solar PV on renewables-dominated distribution grids. And finally, we're joined by Sunny Eliboa. He's the Senior VP and Chief Strategy and Sustainability Officer at Exelon, where he's responsible for the development of an integrated strategy that addresses jurisdictional trends across our operating companies, coupling Exelon's growth with the needs of its customers, regulators, and communities. In this role, he's also responsible for the development of Exelon's sustainability strategy, including the Path to Clean, and he leads Exelon's efforts to evaluate and advance technology, policy, and regulatory transformations required to meet a net zero greenhouse gas goal by 2050. So with that, we're going to have about 10 minutes of presentation from Pablo and Matt talking about the transmission and distribution systems. And then we're going to have some response from Sunny giving the utility view of grid modernization and artificial intelligence. And then I already have questions from the audience, but I expect that our conversation will generate many more. So please use the Q&A function down below to enter your questions, and I will ask our panelists at the end of our discussion. So with that, let me turn the floor over to Pablo.
Thank you, Karen. Let me start sharing. So hopefully you can all see my screen. So I will talk about transmission, and Karen, thank you for providing an overview of how the power system is structured. Transmission, making an analogy with transportation, transmission is the equivalent of the highway network. It enables companies to move bulk power over long distances. So the transmission grid today is operated as a static and passive asset. The main approach to manage congestion on the grid is equivalent to, and you will hear me refer to transportation quite frequently, these are good analogies, will be equivalent to just increasing the tolls or make it more expensive for those transactions to occur. Physically, what that means is the reduction of production from low cost and low emissions resources upstream of a bottleneck, and increasing production of more expensive and typically more polluting resources downstream. So that change in the production pattern to manage congestion costs globally society about $36 billion US per year, and that's a range that varies with the relative cost of fuels. It also has impacts on reliability and resilience, leads to frequent overloads, this can lead to outages during extreme events that are occurring more and more frequently. And it has also impacts in the amount of clean energy that can be available, that can be injected on the grid. So that's the technical term is curtailment, leads to 2 to 17% renewable curtailment. And these metrics are not improving. If anything, it's the other way around. You see on this slide a 4x increase in the cost of managing congestion in the UK over the last decade, as the UK power system was decarbonized. So this is an important, very important aspect of enabling the energy transition. So before we talk about the analytical work and the aspects, a little bit of background. What causes grid capacity limitations? At the high level, these are two factors that cause them. One is the physical capacity. Usually, these are mechanical properties or thermal properties of individual assets, typically limiting the maximum temperature that the asset can operate at, for example, to limit the amount of sagging. And the second aspect is the network topology that defines the connectivity of different elements as well as their electrical characteristics. So with that background covered, going back to our analogy with transportation, the transmission grid has a fixed capacity similar to roads or railways. In terms of the number of cars or trains that can go through at any point in time. But very similarly to the fact that advancements in maps and GPS technology, including AI and machine learning and additional sensors, so on and so forth, have allowed the safer and easier, more efficient driving on those same infrastructures. They're very similar technologies that do the same for the transmission grid, and these are called grid enhancing technologies. Today I'll talk about three of them: dynamic line ratings, power flow control, and topology optimization. So doing an overview first with dynamic line ratings, the first technology. The historical practice has been to set the maximal capacity of an individual asset using conservative assumptions that would accommodate most conditions. These individual limits are called ratings. That's the R and the SLR and DLR acronyms. These assumptions can be quite conservative. Now, if one has the sensors and has data and the ability to process that, rather than relying on year-round or even seasonal ratings that are quite conservative, one can derive real-time or dynamic line ratings using information from the line temperature, the sagging, the ambient conditions, position of the conductors, and so on and so forth. what's the impact of that? The impact can be quite significant. Typically a 5 to 25% increase in the ability of that same asset to transfer power safely based on those measurements. There's also applications to use that data for forecasting, to understand what the capacity would be, not only real time, but a few hours ahead of time, tomorrow and so on and so forth. One quick comment on a key driver of this impact is wind. Very similarly to the fact that even during a hot day, when you place yourself in front of a fan, you cool off. Whenever it's windy, that wind can really cool down the overhead transmission lines. So this is the first technology. The second technology that I'll talk about is power flow control. With the grid operated as a static and passive asset, usually there is congestion, and this you can see on the left-hand side. There can be congestion on the grid, even though most of the assets may have a fair amount of additional capacity, being with low utilization. Now on the right-hand side, you can see the impacts of flow control devices. What these devices would do is they would use the laws of physics to make it harder, increasing the impedance, make it harder for flow to go on the congested path, and then making it easier to flow on the remaining paths that have additional capacity. So these are device-driven flow control that of course relies on sensor information and optimization for their individual controls. The third technology that I'll talk about today is transmission topology optimization. This is a technology that was developed here at BU a few years ago. The objective is very similar to the power flow control problem that I mentioned in the previous slide, but the means to achieve that flow control is different. It relies on opening or closing circuit breaker equipment that is already placed and can be controlled remotely. It's already existing on the grid. So the technology would find reconfigurations of those breakers to reroute flow around congested elements, similar to, for example, what a GPS app would provide when you're driving and get on a bottleneck. It may be better to go around it and save time than take the shortest path, which would be equivalent to the path of least resistance. So what's the impact of both topology optimization and power flow control? Based on a number of studies, the impacts can be also quite large on very large interface transfers. It increases in 3, 5, 10, even more, 12, 15% additional capacity on the existing over the existing wires. Looking at individual bottlenecks more localized, the impact can be even higher, on the even up to 50% under some specific conditions. So I'll close with a couple of comments on the overall impacts from a society point of view of combining all of these approaches and technologies. There was a study done by Brado, supported by the World Coalition, on what the impact of these technologies would be if one looks at the renewable development in 2 states. This is picked to be high potential states, Kansas and Oklahoma, looking for representative conditions. How much additional capacity could be developed economically out of projects that already exist, but it would not develop due to limitations on transmission? And the findings were very impressive. Twice the amount of additional new renewables could be developed on the existing core infrastructure or core transmission infrastructure, as compared to the status quo case. That has very significant impacts both on the economic front, over $5 billion per year if one extrapolates annually, in terms of reduced production costs. Those are savings to society. And on the environmental front, 90 million tons of reduced carbon emissions, just to get a reference of how much that is. That's enough to offset all new cars sold in the US in a year. So very, very large impacts, as well as local benefits. So with this, I will pause and turn it over to Karen. Looking forward to the rest of the panel.
Thank you, Pablo. And now I'm going to turn to Matt to talk about the distribution system.
Sorry, can everyone hear me now?
Yes, we can.
So first of all, thank you for the introduction. So the theme of today's discussion is AI's role in building a smart power grid. And so before sort of diving into where AI fits into this picture, I wanted to just take a minute to give my perspective on sort of what I see as the key challenges, sort of a broader electric power system as a whole, and then how that sits in the distribution system. And so the distribution system, just taking Pablo's transportation analogy a step further, we're the local streets once you get off the highway. So electrically, it's everything downstream of the substation. So the wires that bring power from the substation to your homes or businesses. So at a very big picture, I'd frame the challenge for the industry as a whole is to transition to a cleaner, more resilient, and more cost-effective energy system. So then at the distribution level, this really requires a step change in our ability to host distributed energy resources. And so this is a big challenge, and there's a few drivers for why we need to be able to do this. The first has to do with increasing penetration of solar power in particular. So right now we live in a world where most places it's a few percent of peak load on a local network, and we need to move to a situation in which solar might comprise 50%, even 100% of the peak load on a network. So how do we handle that? Electric vehicles. So right now they're a couple percent of new vehicle sales. So when we start to live in a world where it's that's a sizable percentage of the on-road fleet, that's going to be a huge source of distributed demand that we haven't traditionally had to handle. And then there's also a push in a lot of places to increase electrification of space heating, essentially getting off of natural gas. And so this is, again, another huge source of demand, also tends to be winter peaking instead of summer peaking. So these are three big trends. They're sort of all characterized in a loose sense by the fact they're hard to predict. They're intermittent, and now they're distributed on our distribution networks. There's at the same time sort of the increasing penetration of all these distributed energy resources. It enables to start to think about how to use integrated portfolios of DERs to provide grid-facing services. And so there's a lot of enabling technologies that can let this happen. So improved situational awareness, two-way communication of devices, increased use of energy storage, and load flexibility. So in particular here, I'm talking about traditional thermostatic loads. So these would be a good example is air conditioning. Could be a heating system, a hot water heating system. These are things that that have a lot of inertia. So you have a decent amount of room to use them at different times of day in an intelligent fashion. So you get a lot of load flexibility. They also tend to be quite large loads. So on a lot of homes, air conditioning can be 40% of your summertime load. Space heating in winter, similar percentage. EVs also provide a great potential source of load flexibility. So what all this means is that we have potentially this unprecedented ability to sort of shape load both temporally and spatially. What I mean by that is we can, within seconds or over the course of hours, we can potentially at a highly localized degree, we can decide where and how we're using power. So you can see here there's sort of this big challenge related to kind of the intermittent distributed nature of all of these DERs. There's also this opportunity that this can be a real opportunity to make our power system very localized and responsive, which can help with resiliency. Potentially, it can be very cost efficient, and of course, it's as we're getting more and more renewables, we're decreasing the environmental footprint of the power system. But so what you have here, though, are a lot of components that really need to be intelligently orchestrated to achieve this sort of broader goal. And they're not particularly useful on their own, and that's really where AI comes in. So ahead of the webinar, Karen had sent a few questions to help the panelists from the discussion. One of them was what do we mean by AI? And I put some thought into this and sort of came up with the definition this is a smart definition of AI in the context of the smart power grid. So I've defined it as the ability to automatically collect, process, integrate, and act on information in a timely and near optimal fashion. And this is an intentionally somewhat broad and possibly more mundane definition than normally one thinks of HAL from 2001 or something very sophisticated. And I think in the context of the power grid, which it's a huge legacy system that's traditionally been characterized by a lot of one-way information flows, one-way power flows. A lot of the challenge is the sort of like this pipeline of data that needs to get to something that can act on it intelligently. And so just to bring this back to a concrete example, so we had a pilot project that we completed in 2019, funded by the Department of Energy, the Sustainable and Holistic Integration of Energy Storage and Solar PV. So that's the acronym is SHINES. And so essentially, just looking at the picture on the left here, we've got the blue block here is a typical load shape for a commercial distribution feeder with no solar on it. You bring in solar, you get the sort of orange outline here, which is the traditional what we call the duck curve. So you have a late evening peak that's very peaky. You have large reverse power flows during the day, and potentially there's a lot of additional intermittency that's not really characterized on this figure, but the power might be changing minute to minute as well. So in this project, we were essentially deploying a virtual power plant on a distribution system in Western Massachusetts. And we're using energy storage, solar, and building load flexibility to shape load on the distribution system. And the sort of single biggest takeaway from the project was that we found that the highest leverage, highest point of leverage we had in this whole system was the degree to which we could predict what was going to happen on sort of a rolling 24-hour basis. And the reason for that is, both our energy storage and our load flexibility, those are energy limited resources, meaning once you run out, you're out. And if you think about it, if your goal is to shave the peak, this late afternoon or evening peak, if you're off by a little bit with how you use your energy storage, then there's a huge downside potential where you might be off by a small amount and you set a new peak that's looks more or less like you didn't have an energy storage system at all. What that means is if you're doing a bad job of predicting what's going to happen, you need to carry a pretty big reserve margin on your storage system. So what we found is if you could go back and see the future perfectly, that was essentially worth anywhere from 20 to 40% of energy storage, right? So in other words, you need to upsize your energy storage by a lot of cases nearly 1.5 times in order to account for the difference between perfect information and a very brute force sort of rules-based operations approach. The work we did, which was essentially, we tested quite a few different approaches, and in fact found that predictions based on the simple linear regression approach was very effective. It got 90% of the way there. And so in a lot of ways, the point is less about the sophistication of the backend algorithm and more the idea that we're able to get the data, we're able to get good data, we're able to process it, we're able to do something with it. That's kind of the key point. And so one way to think about that, I like to think about the sort of pithy way of putting this would be that the cheapest form of energy storage would be a really good set of predictions. And so just taking this sort of out big picture one step, this is one particular example application. We can start to think about how the sort of increasing use of data and analytics and artificial intelligence fits in all throughout the operation of the distribution system. And so, from the point of view of something like customer engagement, once you have lots of smart grid data, smart meter data, you can start to predict things like customer uptake of different renewable technologies, distributed energy storage, electric vehicles. So you can use that for planning purposes. You can also start to be a lot more sophisticated about how you do interconnection planning. So a key challenge with getting solar sited has to do with the actual interconnection process. Utilities tend to have to be very, very conservative about how they sort of approach that. As you get more and more confidence about what's going to happen and when it's going to happen, then you can start to be more aggressive in siting more renewables, allowing more things on your distribution network. And then there's this example is from the operations point of view. And so the common theme here is this sort of ability to get data, use that to sort of understand what's going to happen, and then rapidly make a decision into the future about what you're doing with it. So that's essentially what I see as the common theme in these and how AI sort of fits in the world of the distribution system. And with that, I'll stop and I think turn it over to Sunny.
Thanks, Matt. That was great. I have a lot of questions from that. So, Sunny, your reaction from your seat as the technology and innovation and sustainability lead at Exelon.
Yeah, thank you. I hope everyone can hear me clearly.
Yes.
Right. So I think there's a broad agreement amongst the three of us so far that AI will play a role. And I think we've all sort of laid out a common vision on how we see the grid evolving. But I wanted to take just one step back, and it's a little bit, I like being the guy who reacts to this because I think there's some perspective that I can provide as to why we're seeing what we're seeing today. And that sort of fits into my role as the sustainability officer at Exelon. Karen talked about the utilities being such an old business, about 150 years old, give or take. Exelon has probably the oldest utility in the US. I think Baltimore Gas and Electric, which is one of our utilities, is about 150 years old. So we have a strong legacy of understanding the evolution of what has happened over time with the electric industry. We have about 10 million customers. We're present in large urban centers like Philadelphia, DC, Chicago, and Baltimore. And our perspective has been that the grid is central to a lot of things that actually drives the economy. And that's why the sustainability aspect of it is really critical. Now, the discussions we've had here so far talks about, how the grid is changing, but the most important thing is, why is the grid changing? The grid is changing to advance, what we call an imperative to help manage the planet. The biggest challenge that we have today is, climate change. And the grid has been seen as a very useful tool to help us achieve decarbonization, which we feel is necessary for us to address climate change, either by an adaptation methodology where we're talking about things like resilience, or, for mitigation, where we're trying to reduce the amount of greenhouse gases that we put out in the atmosphere due to our various economic processes. So this push towards decarbonization results in us trying to think about newer ways, better ways to utilize the grid. And for the most part, everyone agrees that the pillars for decarbonization are pretty much the same. It's, figuring out ways to clean up the grid, utilizing the grid in the most efficient manner, driving that electricity towards all economic processes, and then ultimately, when you can't do that, looking for clean fuels to essentially address areas that are hard to decarbonize. So things like electrification, things like energy efficiency, things like clean energy resources or clean distributed energy resources actually become the mainstay of the grid. And as you incorporate all of these things, it means you have to somewhat think differently about how you manage the grid. I know we've been talking a little bit about the role of AI and, its role in sustainability and managing the grid. But in simple terms, how would you define AI? I think about AI as algorithms that figure out things without specifically being programmed to do so. They're not being explicitly programmed to provide a certain function. So in essence, it can give you an output B, but it doesn't necessarily have to be given an input A. It could be given multiple inputs. As a result of that, they're more robust, around the edge cases. So things that are not traditional, AI actually helps you with that. And they evolve as conditions change, and they get better with time. So as conditions change, they're able to make dispassionate decisions based on data that's available. And as they expose to more data, they get trained over time and they can make these decisions better. So time could actually benefit, AI. Machine learning is a major subtype of AI that I think we have many uses in our data-rich environment. One of the things that is actually shaping the electric space today is this convergence of, data-driven technologies and hard physical assets. So as you think about all the infrastructure we have on the grid, they actually provide a little bit more data. They give us, situational data. They give us performance data. They give us a lot of data that we actually need to use. And we've talked about things like, spatial and temporal granularity, how you need to have time series data and how you need to have locational data to know what asset is doing what, when, and all of that. But to make sense of this, you need some sort of ability to have an algorithm that helps you explore and, for want of a better word, recognize nuanced patterns in highly complex systems, which is what the electric grid is. And, as you provide access to these data sets, ML as well begins to get a little bit better. So just from their definition, you can tell that they have a role to play in, the grid. One of the biggest challenges that we face with, this push towards decarbonization and climate change is there is a need to have better weather data. We've been talking about increased intensity and frequency of extreme weather events. The IPCC, the Intergovernmental Panel on Climate Change, I think issued another report about 2 weeks ago. And in that report, it talked about the fact that we're not doing enough, or we're not doing it quick enough, and things are getting worse, and we're affecting biodiversity. the birds, the bees, they're all adapting, whether it's polar bears or honeybees, they're all, Darwinism is happening in real time. It talks about things like, water security, because of these changes in precipitation patterns, water security is going to be important. But the third thing it talks about is the need for climate resilience. And this climate resilience is actually well integrated into the electric grid, because the electric grid basically is going to be the backbone of this push towards decarbonization. And so machine learning is one of those areas that we can actually use a model to actually help us predict, accurate weather, depending on time of day, and begin to understand how load varies, because we have better understanding of weather patterns, we have better understanding of time of day fluctuations, and we can actually begin to see some correlation with that as it shows up on the load or the demand side, and how we match that with the supply side of energy. So from my perspective, and just listening to all that has been said today, before we get into the questions, the key functionalities that I think AI and machine learning can do for us is it will help us get a better understanding of what is happening, on the grid. It can help us predict what will happen on the grid. And to some extent, it can help us make more optimal decisions about how best to operate the grid. And we can talk about this a little bit later, and we can always talk about examples of it. But, in terms of assessing what is happening, it's almost, I would say, virtually impossible to accurately measure everything that is going on the grid. Sometimes you have, in fact, most times you have data quality issues, either missing data or misclassified data. We talked about us being in the business for about 150 years. It's virtually sometimes impossible for you to eliminate human error. Maybe you have an asset that is tagged a certain way, but on the system, the location of the asset has been moved, or someone has, basically, recoded it wrongly. Machine learning begins to help us, go through, bulk data, identify missing gaps, sometimes help us plug those missing gaps, and help us with anomaly detection. So sometimes you see things like, when there's a change in a feeder, you have to ask yourself at the distribution level, is that as a result of a problem, or is that as a result of just a misclassification of data? Sometimes you can see things like, changes in voltage patterns, and machine learning can help us figure out, like, okay, was there a cloud that just went over and, we saw like solar generation drop a little bit, and that's what we're seeing on the system? Or, was it something more? In other instances, it could be things like, you see certain data pattern and you say, well, this could be evidence of a cyber intrusion. So, is this real, or do we need to explore this a little bit? So that situational awareness and the ability to absorb large chunks of data and make sense out of it is very important to, essentially address, what we think is going on with the grid. It could also help us predict what will happen. It could also help us make us better decisions on how to optimize the grid. We've done a lot of predictive maintenance that is driven by just understanding data from like different assets on the field, performance data for things like transformers. At one of our subsidiaries like Pico, we were able to utilize, predictive analytics to say, hey, based on the performance of certain transformers, they are likely to fail, and therefore we need to go in and essentially, swap out some of this potentially assets that could fail, and understand how we can actually bake reliability and resilience into our operations. So all of this based on the fact that, we are able to leverage large chunks of data. It's useful because we're able to have that interaction to utilize this data in a manner that is most efficient. But I would want to sort of pause here and go into the questions by leaving us with one key thought, which is, as great as AI and machine learning could be for the grid, there's always a need for some sort of human behavior and the ability to learn by interaction. So while some of these tools are helping us make better decisions, they would also be better if they can actually work closely with the human interface. They're essentially still tools, and there still will be a significant amount of judgment based on experience that needs to happen on the grid. And that interaction between humans and machines will be a key aspect in helping us managing the grid going further. So with that, I think I'll pause here and try and open it up for a little bit more of an interaction, and we can talk a little bit more about like specific use cases and things like that.
Thanks.
Karen?
Matt and Pablo, go ahead and turn your cameras back on. I thought, Matt, you said you were making reference to using basic regression analysis to look at some of the data, and I thought that was really interesting that you were drawing a distinction between the quality of the data and the sophistication of the algorithm. And I once saw a statistic that 85% of the data or more that gets generated worldwide, not just on the grid, never gets examined at all. But when we're talking about the grid, we've got sensors and equipment generating massive amounts of data, and it's being generated from the millisecond to much larger time intervals like weeks and months. If you look at the markets and you look at climate planning and the data that gets analyzed. Can you all talk a little bit about where on the grid the AI is going to be analyzing the data that gets generated? Because I think people may assume it's all going to happen in the cloud. Let's start with Pablo, if you have an opinion on that.
Yeah, I think there will be different locations, but also different roles. In the transmission level, I think that could happen on the cloud for some applications. It may happen also in the control centers for more operational, closer to real-time applications. So I see a variety that may depend on the specifics of the application. But I'll be very interested in Suni's opinion on that, since he's on the side.
Yeah, no, I think it's going to be all over the grid. I think that there will be a portion of it that would be a little bit more centralized. I think that it's going to be used mostly for things like forecasting, DER adoption, flexible load production. All of that could be a little bit more centralized, and you could actually utilize AI in that regard. But then there would be a lot of, because of just this proliferation of DER, I think there will be a lot more AI at the edge. I think a lot of the grid edge technologies would have the need for us to do everything from sense to process to actuate. So essentially, management of like this grid edge devices and the connection with the grid would be a really good place for AI to begin to take a hold. We've been talking a lot about vehicle grid interaction. In some instances, you need to understand how best to optimally charge a vehicle. And if you're trying to solve for something like a climate goal, it's a function of so many things. A function of like, what the grid demands are at that time. It's a function of price. It's a function of the marginal asset that you need to call on in terms of like what the grid emissions rate could look like at the point that you're charging. It's a function of so many things, including the asset performance itself of the battery of the vehicle. So something like machine learning and AI for sector coupling, like between electric and the transportation sector, could happen at the grid edge. Something like AI for the purposes of just grid management and essentially ensuring that this combination of reliability and resilience built into the grid could be more centralized in terms of like planning load and forecasting what the implications of demand and supply mix needs to look like.
Matt, anything to add?
Yeah. I mean, I think the answer is it depends. But so there's three issues. I was just trying to frame this. So three issues with sort of pushing everything to the cloud. Just off the top of my head, one is latency. So it takes time to send data someplace, process it, and then send it back. A second is there's a cost associated with that in terms of bandwidth. It's not trivial. I've sort of always been surprised. A lot of solar providers don't, like having a cell modem at a site, that's expensive, and you're maintaining that, right? So there's a bandwidth cost, and then there's a sort of cybersecurity and privacy implication once something leaves the site. So essentially, I'd say you want to push as much intelligence as you can to the edge, right, and have devices that can make autonomous decisions at the edge locally, and then push what you need to into the cloud. And usually that would have to do with things that don't need to respond very quickly, might not have as much of a security concern, and where you can sort of, I'd say, distill data down to, instead of sending every, say 1 second resolution data, maybe you're sending updates every 15 minutes, every hour, or something like that.
That's great. So kind of following on, I've got a question from the audience about your view on transactive grid and what the role of AI would be in a properly structured kind of transactive grid, and how it might play, how that transactive nature of the grid would play a big role in congestion issues while promoting clean or resilient distributed energy resources.
You want me to?
Throwing it out there. Go ahead and start, Matt.
Sure. So I guess just for context, so there's an idea of a transactive energy system where at its most, there's a very micro version of this where essentially the level of individual homes or even devices, you essentially have an open market for trading energy on a highly localized, very fast time scale. So so I might have solar on my house, my neighbor doesn't, and I'd say I can get I'll sell you energy for X amount, and they'll say, great, I'll take it. So that's sort of like the premise of a transactive energy system. So what's the role? I guess I'm like somewhat skeptical that we would ever that it will ever make sense to get to that point. And this is sort of a personal opinion, and there's lots of people that disagree with that. There's a basic logistical question, which is that the utility owns the wires between houses, and so like anytime energy is going on wires, utility has a role in that. And so there's sort of a middleman, or not a middleman, but like there's an entity there that makes it all a little bit challenging. Then there's just transaction costs and the sort of share of one's pocketbook that's associated with sort of energy transactions is fairly small in the grand scheme of things in general. So once you start laying in the sort of overhead you need to have to make that practical, it makes me skeptical of this very like the ultimate house to house version of transactive energy. Now, taking a step back, if you say, is there a role for what I would call a distribution, like marketplaces on the distribution system? I'd say absolutely. And so it's just a question of bringing the scale out a little bit. So I can see some of these issues are a lot easier to address once you're looking at the neighborhood, the distribution level, where you might have one entity that say a large customer might have a load shaping service they could provide, and someone else might offtake it. Like that kind of thing, it's a lot more feasible than every house sort of running their own private energy exchange. But that's just sort of my point of view.
Sunny, I love your perspective on that.
It's interesting, but I think Matt's points are we're in somewhat of an agreement, and the agreement there is, I think the transactive grid at the micro level is difficult, and it's not just because there's a utility in between, it's because the infrastructure hasn't been established For instance, how do you, there's going to be a physical and a financial settlement that needs to happen when you move power from one person to the other. A lot of that hasn't been thought through, right? So it's almost like you need to have a means to say, well, electrons were delivered, and this is the cost of that electron. Someone needs to price that out. Someone needs to have a settlement. There's been a lot of discussions about using a distributed ledger to do so. And I think those issues are still issues that need to be worked out. Now, when you elevate that and you talk about it almost at the distribution level, yes, you're right. And the question becomes things like, the industry framework. Do you need to have a network operator or distribution services systems operator? Like a network owner or systems operator, what will be the role of the utility at that point? You're right, because at that point, it's easy to be able to have some sort of aggregation. It's easy to be able to find opportunities to match. And it's also easy for you to use existing signals to give, like the right incentives. And utilities tend to try to do that in things like program designs and rate structures. So when you get into like the distribution level, and I know that customer X putting a solar panel on this particular feeder is actually more beneficial for the system than putting it on another feeder, we would like to give the right incentives to say, hey, well, I think your assets that you're about to incorporate on the grid has more grid benefit and therefore should be in this particular location. And that begins to create this opportunity to monetize third-party owned devices that actually support grid reliability and resilience, and begins to come to the edge of the distributed, managing the grid from a transactive energy purposes. But I do want to continue to point out that for transactive energy to work at the grid, there's so many things that the bulk system does really well. It can understand things like market manipulation. You can't have a bunch of folks who own a solar panel in a neighborhood decide to shut off their solar power because they think that, the grid will up the prices, and they can actually, it can be more beneficial for them to curtail supply, at the distribution level, because it actually favors them. And who monitors things like that? So there's so many things that need to happen before transactive energy actually takes root. But I do think that we're definitely on the cusp of it. I do think that machine learning, AI can actually help us, coalesce a lot of the different pieces of, market signals that need to facilitate this. But even more importantly, I think that there needs to be a clear system by which those signals are, sort of like monitored, transferred, traded upon, and ultimately cleared. But ultimately, I think we'll get there over time.
Thank you. That was very interesting. That's a big question I've been wondering about. But there's a question specifically for you, Pablo, about optimization. And apart from optimization, these grid enhancing technologies on the transmission side, can you talk a little bit about the impact that these AI powered technologies will have on sustainability?
Yeah, I touched a little bit. Go for it.
Yeah, go for it.
I touched a little bit in the presentation. I think it goes back to the one of the opening statements from Suni. What do we want out of this energy transition? What's the purpose of it? And the purpose is to decarbonize, increase resilience, and so on and so forth. And at the core, that would require transferring more power over the grid, and that could be at the relatively local level. We were just talking about the grid edge, but if you're talking about very large events in moving lots of power from one region to the next, that's squarely within the transmission realm. So when one talks about optimizing the transmission network, it's actually what is the purpose of it? It's all of the above. Under normal conditions, it would be, for example, reducing the cost to consumers, enabling more efficient units to run instead of more expensive ones. But the minute you start increasing renewable production and there are bottlenecks in historically, the level of curtailments can be quite significant when those bottlenecks appear. 2 to 17% annually. Those are large numbers. By optimizing, if you can unlock a fraction of that, even that's a big sustainability benefit. And then going to the next step on the development side or the planning side, if one could speed up the energy transition by unlocking transmission capacity and enabling more renewable projects faster on the grid, that's again a great sustainability play. So those are the few examples of the sustainability benefits.
That's great. Thank you. Well, I think we've reached the hour, and I'd want to remind people, if you could, Sydney, put the slide deck back up, that there are 2 more scheduled webinars in this artificial intelligence series. We've got one scheduled for e-mobility on April 29th, and on June 3rd, a discussion on smart homes and energy justice and the role of AI in contributing to smart homes and equity. So thank you very much to my panelists and to Boston University for hosting us, and we look forward to the next discussion in our series. The slide deck will be available, and the recording will also be available. So we look forward to continued engagement with you. Thank you.